We're going to finish up Thermo today. There is a small typo in the reaction. Can you tell me where the typo is? The W. What's it supposed to be? It's supposed to be an arrow. No, it is tungsten, but that's not supposed to be a W. It's supposed to be an arrow. It's supposed to be iron plus oxygen yields. I don't know. It's a typo. All right. So here's my question. This is very simple, and again, I'm doing this right now in honors, Kim, so I would expect you guys to be able to do it. And this, I want you to write down, please, no one blurt this out. No one blurt this out. Do not say this out loud. Do not blurt it out loud. Write the name of that thing right there. Again, write it down. Dadgum. Write the name of that thing down. That scares me that you are all looking at me with blank stares. Shh. The last one, the compound. I hope you know Fe is iron and O2 is oxygen, but I don't know if you know what Fe2O3 is. Shh. I'm teaching this right now in honors. I would expect you guys to be able to get through this. Yeah, I'm way behind. I hope so. I don't know. No, honestly, what it was. Alright, so this is what you should have gotten. That's what you should have gotten. You should have gotten iron 3 oxide. Alright, now, my next question is, the question says, use the following data to calculate the equilibrium constant. So this is exactly what we talked about yesterday. Look at what all they gave you, and I wish I should have taken this and left it off, because this is going to be a multi-step problem if this were a free response question. It specifically says calculate the equilibrium constant, but the only data they give you is delta H and S. That's it. That's the only data they give you this entire problem. So how can you go from H and S all the way to K? Okay, so you've got to find delta H of the reaction. Then, hang on, guys, hang on. You got to do delta H of the reaction. You got to do delta S of the reaction. Then you got to do delta G of the reaction, and then take G and convert it all the way to K. So there's a lot of steps going on here. So what I want to do is I want to look at all three of them. Excuse me, all four of them. So the first thing I want to do is I will need your help in solving for the delta. Actually, as a matter of fact, let me erase this. So we have, oh my gosh. What? 4F? That doesn't sound right, but we'll go with it. Okay, that is right. That does make sense now. I'm with you. All right, so they tell you that we need the delta H of the reaction is going to be, and I'm just going to go ahead and simplify it. First of all, they told you that this was a solid, right? This was a gas, right? And this was a solid. That's right, because iron 3 oxide. So here's the crazy part. If you go back and you look at this table, two things in here are zeros. Why? They're in the normal solid natural state, okay? So the only thing that we're going to have in here is the two Fe2O3s. That's it. Why don't I have to subtract anything from it? Because both of those are both zeros, so there's not going to be anything to subtract it from. Now, what was the value for Fe2O3 was negative 826. What is negative 826 doubled? Okay. All right, so delta H of the reaction is equal to negative 1652. Now, how do you get the unit for this thing? Look at the table right there. It tells you kilojoules per mole of reaction. All right, so this is kilojoules per mole of reaction. Now, the second one Now we've got to do delta S of the reaction. But the problem with delta S of the reaction, are any of those values 0? No. Why can't you have a 0? Very good. Everything has disorder unless you're at absolute 0 and it's a perfect crystal, which does not exist. All right, so we've got 2 Fe2O3s minus 4 Fe's plus 3 O2s. Let me ask you something. Never mind, that's a bad question. I'm going to go back to the table. Go. What's wrong? I promise I'll come right back to this. I promise. Of the 3 in this particular question, which one of the 3 has the least disorder? Least disorder. Iron solid. Why? It's the least number. That was my next question. Numerically, it's because it's the least positive. But state of matter wise, why? It's a solid. Now, but also iron 2 oxide is a solid. Why is it more disordered than just plain old regular iron? There's more electrons. That's the key right there. Because remember, electrons create disorder. So that's why it is more disorganized. Now, when we go back here, I know that, help me out because I'm not looking at that sheet. What is the iron 2 oxide? It was 97, right? 90, okay? So 2 times 90 minus 4 times what was iron? 27 plus 3 times what's oxygen? 205. So again, it's not hard, but you just have to do the calculations, and that can get a little cumbersome. Two times the number in the delta H. It's like, are the answers on the bottom of this slide? Unfortunate. Sarah, there's a high probability in that. What's the answer? All right, negative 542, and the unit is joules per molk. Molk. Huh? 43, my bad. Negative 543. Yes. Now, here's the deal. So my question is, which one of these two, delta H or delta S, is nature agreeing with or liking? The delta H. Why? Because this is exo, and the negative one is going to be what? More order. Well, nature does not like that. How can you look at the reaction and tell it's going to more order? Very good. You've got 4 moles of a solid and 3 moles of a gas condensing all into 2 moles of a solid. That's taking a lot and putting it into a little bit of space, okay? And so that's why there's going to be a lot of order going on in the system. So remember, the key factor in determining if this thing is going to be spontaneous or not is what? Because this one tells it it's thermodynamic, but delta S says it's not thermodynamic. But what's the only 3 things that tell you if it is thermodynamic or not? GEK, G, E, and K, okay? So we've got to determine how, depending on the temperature, if it is or not. So that flips us into this. So now we've got to do delta G equals delta H minus T delta S. All right? Now, the delta H value was... Why do I keep hitting that button? Now, here's the problem. That's right, guys. And I'm telling you, that's going to get you if you don't pay attention to it. The units, kilojoules. Personally, because that's a larger number, I may actually convert this to kilojoules this time, just to show you that I can do it both ways, and I'm tired of hitting that button. So it's negative, what was it again? I keep remembering. 1652. All right, 16 52 kilojoules per mole of reaction minus T, and it says it is 25 degrees Celsius, but what do we have to put it in? Kelvin, so 298 Kelvin, and then it's it's negative 0.54 what? 543? 543 kilojoules per mole. Okay. Now, will any of the units cancel? Kelvin. So that what you're going to get left is with what? Kilojoules per mole. Okay. Either one. It does not matter. If you convert it to joules, leave it joules. If you convert it to Kelvin or kilojoules, leave it in kilojoules. So when you do the math here, for our answer, does anyone get this in kilojoules? Is this going to be a positive number or a negative number just by looking at it? It's going to be a negative number because the delta H is more negative than, nope, that's not the right place, than the T delta S. What? One. That? Sir. It's a great question. What unit do I have written on the one you see right there in front of you? What unit do you have written? Look at the table. So it's joules. I converted it to kilojoules. Why did I have to convert it to kilojoules? Because their delta H was in kilojoules. Could you have converted the 1652 to joules? Yes. You have to convert one to the other. Doesn't matter which one you go to. Now, say that again. I wrote it down wrong. It was 543. That was my mistake. All right. Now, so is this reaction thermodynamically favorable or not? Yes, it is thermodynamically favorable. So here's the deal. The question, we're still not finished with this question. Now again, I've already told you that this will not be one question. This will be multi-steps, and it will ask you to do different things. But the next part asked us to calculate the equilibrium constant. Matter of fact, let me just do it over here. So delta G equals negative RT ln of K. And yesterday we talked about this. Remember, K is equal to the inverse of the natural log of delta G over negative RT. That's just the algebra setup of this thing. I'm going to go ahead and forewarn you. Can you plug in this number right here exactly as it's written into that? Why not? Very good. And what thing is going to mess us up if we leave it in kilojoules? The R. The energy R. Very good. So what we need to do now is we need to rewrite this. So E is equal to negative what? What is G? Yep. Why do I keep hitting the wrong button? Alright, so it's 1,490,000 joules. And again, I just mentioned this. The reason we got to convert it back to joules is because of the energy R, which is 8.31 joules per mole. And the temperature is 298 Kelvin. Now, you already know this from working with us for a long, long time. What do we like the unit of K to be? Nothing. We don't want anything. So, do our units cancel? Joules, well, that's the wrong color. Joules cancels, moles cancels, and Kelvin cancel, giving us no units there. So what? It should be super huge. Are you serious? Are you serious? Hold on 1 second. Hold on. Hang on. Hang on. Whoa, notice what it says. It's not an error. It is an overflow. What? I don't care. The whole point is that as long as you can set it up. So what was the answer? Shh, 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 stop screaming. So, how thermodynamically favorable is this? Okay. All right. So, naturally, here's the strange part. What is iron plus oxygen? What? Rust. Do things naturally rust? That's rust. Okay. Rust naturally on its own forms. All you need is a little bit of water, a little bit of oxygen, and it'll form. So that's why it's so thermodynamically favorable. All right. The last thing that we could not do yesterday that I do want to actually do yesterday is do this one. So delta G equals negative Fe. Because here's the deal with this one. With Fe plus O2 going to Fe2O3, you can, listen guys, you can set up your oxygen rod in red cat OA. I know that it's been a really long time. I want you to set up your halves, find your N, and go from there. Because the reason I'm showing this is because you're going to see it tomorrow. Yeah, but we couldn't do N. You can actually do the N in this one because it's a redox reaction. Thursday. Negative 1490 kilojoules. We actually don't talk to each other. No, remember, you don't have to balance it. You set up your half first. Set up your halves first. What do metals like to go through? Oxidation. Alright. So we got Fe going to Fe2O3. Well, I know that I've got to have two of these. How many waters? Alright, so plus 3 H2Os. How many hydrogens? Plus 6. Alright, so here's the deal. This whole side is what charge? The whole left side, neutral. The whole right side is what? Positive 6, so I need 6 electrons. Cool with that? No. Because we'll balance it out in the end. Alright, so this time we've got O2 going to Fe2O3. So here's the deal. I've got... See, that's the problem. You can't balance that, can you? Your N will be 6 either way, right? For the sake of the problem, let's just go with it. Delta G equals negative Fe. So E, hang on, don't worry about it, Devin. We're just going to move on. So delta G is equal negative N over F. You guys told me that delta G was negative 1490. Yeah, don't worry about that. Per mole of reaction. N, we said, was 6 moles of electrons. And F. Who is F? Not what. Who? Faraday's constant. And what is F? 96,000 what? Excuse me, 96,500 coulombs per mole of electron. It's 496,495. That's the real number. All right, so then you got mole of electrons cancel. No, I didn't. But I wanted y'all to do it just for practice. No. If it asks specifically for voltage and stuff, then yeah. All right, so do that math for me. First question is it going to be positive or negative? Even if you didn't see the math, how do you know it has to be positive? G was negative. E has to be positive, regardless of the numbers. Okay. And remember, what was it? What was E? What is E? Who is E? Cell potential. What is E? A volt, and a volt is a joule per coulomb. But we're actually going to get kilojoules per coulomb this time. That's actually a good point. So So let's change this to negative 149,000, because it's got to be it's like she said, it's got to be a joule per coulomb to technically be a volt. Otherwise, it's a kilovolt. It's a kilovolt. You can. That's what I would do. All right, so negative 149,123 divided by negative 6 times 96,500 close equals that. So it's it's just positive 2.57 volts. Okay. So it's 2.57 joules per coulomb or a volt. So that's what I would do. I would leave it as. So really, if you try to leave it as a kilovolt, it's going to be less than a. This is the best option. Huh? Yes, this converting all this stuff will be. Now, not all in one problem, but multiple parts. Okay. No. All right, so here's actually a really good question. So let's look at this for just a second. And I think this one's going to kind of throw you for a loop, but if you pay attention, it'll make sense. So here's the deal. It says one method of synthesizing methanol, which is C3HOH, involves reacting carbon monoxide and hydrogen gases. Calculate the delta G at 25 degrees Celsius for this reaction where carbon monoxide gas at 5 atmospheres and hydrogen gas at 3 atmospheres are converted to liquid methanol. So what you actually have to do for this one is actually solve for Q and then plug it into negative Ratlink. Yeah, so it's the other way around. So instead of us starting with delta G and getting to K, this time you would actually solve for Q and get to G. Now, let me ask you this question. I hope you can at least do this. Can you solve for Q for that reaction? Don't say it out loud. Just write your basic Q. No numbers, just your Q. Just your basic Q. It's the exact same thing as K. It's just not at equilibrium or standard conditions. That's the only difference. K tells you when everything is at equilibrium. Q is at either side of it. Yes, same exact concept. Because you're thinking about this. If it's at K, then you're at equilibrium. Then G is 0. You with me? There would be no purpose to solve for it. Yeah. Alright, so hopefully what you should have written should have been this. Ooh, no. Whoa, whoa, whoa. I'm actually wrong. No, that's not cotangent. I agree. I agree. I absolutely agree. It's one of those things that it is different, and they have these special rules that you have to make it different, and it is aggravating. There's nothing we can do but just follow the rules and go along with it. So now we've got 1 over carbon monoxide is 5. Hydrogen was 3. And so what you have to do is you have to do 3 squared, which is 9. 9 times 5 is 45, and then take the inverse of 45, which is something. 1 over 45. What is 1 over 45? 0.022. We'll go with 2 sig figs here. Now, that's Q. Then what do you do with Q? Plug it into negative RATWing. So we've got delta G equals negative RT actually Q this time. Okay, so R is negative 8.31 joules per molk. Temperature was 298 Kelvin, and the Ln of 0.022. Yeah, that is the energy constant. Yeah, if you have to use R, you have to use that number. Now, in terms of units, will anything cancel? Kelvins cancel, leaving you with joules per mole, and you could actually throw in the reaction part, which is exactly what delta G wants to be. Now, my question to you is, since Q is less than 1, what should G end up being? Should end up being positive, which means this reaction is not thermodynamically favorable. And let's go back and look at the reaction real quick. Does carbon monoxide in the air naturally combine with the hydrogen in the air that's already floating around and rain methanol down on us? No, that's really bad if it did. So if you just look at what's really chemically happening, you can tell yourself that does not make sense, because what things produce carbon monoxide naturally? Cars. So every time a car cranks it and starts producing carbon monoxide out the back, is there hydrogen floating around in here right now? If it naturally did this, it would rain methanol, which is really freaky. But we know that that does not happen. So did anybody get an answer for this? So positive 9 point what? 9 point. Is that right? Kilojoules. 9.43 kilojoules per mole of reaction. So it takes that amount of energy to get this reaction to even begin. Yes, sir. Yes. Because they're the same things. Because it was 9,430 something, so I just converted it to kilojoules. You don't have to. You can do it. You can do it whatever energy you want to do it in. Me too. So this is kind of a thermo question. Excuse me. This is the first one. All right. Consider the reaction represented above that occurs at 25 degrees Celsius. All reactants and products in their standard states. The value of K is 1.71 times 10 to the 37th. Now, so is that a really big number or a really small number? That's really freaking huge. So, A, predict. That's all it says. Predict the sign of the cell potential. What are the only two options? You have a 50-50 shot. For the cell, based on the reaction, explain your prediction. This should be very, very easy. And I keep telling you, if you know one, you know them all. What is E and Y? Why? Perfect answer. E is positive because the reaction is thermodynamically favorable since K is greater than 1. That's it. That's all you have to know. Now look at B. Predict the sign of delta G for the reaction. Explain your answer. Same thing, but delta G is negative because K is greater than 1. I'm telling you now there's some multiple choice points based on that topic. Do you agree there's a lot of wordiness? Like one of the questions on the multiple choice, I'm telling you this now, is like a paragraph. And it asks you what the signs of E and G are, and all you have to look at is what? What is K? There's a huge paragraph, but it's trying to confuse you. All right, C. If the reaction were carried out at 60 degrees Celsius instead of 25 degrees Celsius, how will the cell potential change justify your answer? Now, kinda. Let me think about the best way to explain this. Yes. Do what? Tell me why. Yeah, but this says how will the cell potential change? This is also true. This is also true. So if you have N Phi equals RT ln of K. So if you do E is equal to RT ln of K all over NF, what's the only variable that's changing? That's the only thing that's going to change because R is a constant, F is a constant, K does not change. Well, K can change with temperature. Remember, the only thing that affects K is temperature. And that the thing my brain is kicking in. I need to know if this reaction is exothermic or endothermic. Not necessarily. And I don't know what the key is for this one. You could. Either way, it's not gonna make a difference. I'm trying to think of mentally how to go about answering this one because I don't have the key. How the sub. All right, E. Let's look at E real quick. When the cell reaction in D reaches equilibrium, what is the cell potential? 0, because the battery becomes dead. How will the cell potential change in the reaction if we're carried out 25 with a 1 molar solution of zinc nitrate and a 1 molar solution of copper? All right, so this one is the Nernst. Remember how we talked about Nernst? So my first question is, if you write Q for this reaction, what would Q look like in that reaction? Very good, right? Why is it zinc over copper? Well, those two are solids. They go away. And why is it not copper over zinc? It's products over reactants, right? You with me? So notice what they said. What if zinc were 1 molar? So we've got 1 point that over 0.1. So in terms of products versus reactants, what is Q now going to be? Is Q going to be greater than 1 or less than 1? All right, so Q is greater than 1. So in terms of K versus Q, we don't necessarily know. Yeah, we do. We do know K, don't we? All right, so K versus Q. Well, you just told me. That's right. That is K for different. No, that. Yep. So remember products versus reactants. What's greater now? The products are greater. So what way is it going to shift? The reactant. So, wait, I wrote that backwards, didn't I? Wow. So in terms of reactants versus products, you told me that the products were greater, so what way is it going to shift? Back towards the reactants, because if you've got too much product, what's it going to want to make? It's going to want to make the react. So what's going to happen to cell potential? It's going to drop. Cell potential should drop. Yes. So Q is then greater than K. Very good point. All right. See, there's a lot of junk involved in here.